Hello, everyone, and welcome to AMAT 812 seminar and analysis. This semester, it will be classical harmonic analysis. So as I mentioned in the syllabus, we're going to be talking about Fourier series, Fourier transform, and the modern tools needed to study these very important objects. All right, so I want to begin with a little introduction to Fourier series. I presume most people have seen it, but in case you haven't seen it, or in case you really forgot kind of what they're all about, that's okay. And I'm not really going to get into the practical applications of Fourier series because there's thousands of books that do that. You can apply it to all different types of sciences and engineering disciplines, mathematical physics, et cetera, et cetera. So, all right, without further ado, let's begin. So let's assume I have a nice function defined on all the real line. Everything I'm going to be doing is formally. For the next maybe 10 or 15 minutes, I'll discuss when I start doing something rigorously. But for now, everything is just formally. So not going to be much rigor for a little bit. So assume f is one periodic, meaning that for any x and any k, x is in the real line, k is an integer, f of x plus k equals f of x. Okay, so somewhat akin to assuming a function has a power series, we're going to assume a function can be written as an infinite series involving sines and cosines. Such a series is called a Fourier series. It's called a Fourier series after Jean-Baptiste Fourier, who he made the assumption that any nice practical function can be written in this way and use that to solve the heat equation like you actually do in undergraduate PDE. It actually irked some people at the time, particularly Lagrange, the assertion that all nice functions have a Fourier series. What does nice even mean? But anyway. And I should mention people like Euler and D'Alembert were among people who earlier used these kinds of expansions, these kinds of infinite series to solve particularly the wave equation, the equation for a plucked string, for example. Same wave equation from your undergraduate PDE course. Okay, so it's a lot easier to deal with complex exponentials than it is to deal with sines and cosines. So writing f in terms of this infinite series with sines and cosines is equivalent to writing f in terms of this expansion, this infinite series with these complex exponentials. Okay, and this is an easy homework to do. There's really not all that much to it. And we can write this in shorthand notation. K equals minus infinity to infinity, ck e to the 2 pi I k x. So in general, whenever you have an infinite series that maybe looks a little funny if you've never seen it before, k equals minus infinity to infinity, all that means is we're looking at k's less than or equal to 0, which means k equals 0 to infinity with minus k plugged in. And then we're looking at positive k's. Okay. And rigorously, this infinite series converges if and only if both of these two, by definition, if both of these two infinite series converge. So. And I should mention even electrical engineering, for example, books, they do Fourier series using complex exponentials because doing any manipulations and computations with them are just so much easier using the properties of exponentials, as we'll see time and time again. All right, so let's get a formula for these coefficients. Okay, and yeah, so I'm not going to be very rigorous here, but that's all right. So what I'm going to do is, and you might have done this in undergraduate differential equations, certainly you do it in undergraduate PDE, but what I'm going to do is multiply both sides of what I circled by e to the minus 2 pi I mx. I'm going to combine these two exponentials together, and then I'm going to integrate both sides of what I have right here. I'm going to integrate both sides of this here. All right, and when I do that, one second. Right. When I integrate both sides, I'm going to interchange sum and integral and pull out the ck. Really, you have to justify that. But anyway, we're just going to assume for now we can do that. And we can write, for this integral on the right-hand side, we can write out this complex exponential in terms of sines and cosines. And we can do this calc 1 integral, and we'll see that this entire integral here collapses into 0 if k is not equal to m, and it's 1 if k equals m. Sorry about that. Not sure why it does that, but anyway. Okay, so that means if the integral collapses to 0 if k is not equal to m, and 1 if k equals m, and remember m is fixed. Okay, so no funny business here. Well, that means the infinite sum has to collapse. And if the infinite sum collapses, well, it just collapses into Cm. It's only 1 if k equals m. 1 times Cm is Cm. So to conclude, we came up with this non-rigorous formula for what Cm we should at least be if a function has a Fourier series. Okay, and it's just this integral 0 to 1 e to the minus 2 pi I mx f of x. Okay, so standard notation, and I'm just going to switch back to k. If we sum over k, we have to use another, constant variable integer. But let's go back to k. Standard notation is f hat of k for any integer k is going to be this integral here, and this is called the Fourier coefficient of f. Right. So everything was non-rigorous here. On the other hand, the arguments we just employed absolutely can be rigorously done if we assume, well, particularly if we have a sequence of a little L1 sequence. So if we have the CKs are in little L1, and if we define f of x to be this function here, which will converge uniformly by a very famous theorem you learned in AMAT 511, and you used in AMAT complex analysis from the really get-go, maybe the first lecture, hint, hint. I mean, if you don't even want to use complex analysis, write this in terms of real and imaginary part, and use this famous theorem for convergence of an infinite series of functions. But anyway, right, so this is going to uniformly converge for every single x, and so f of x is defined for every single x, and the CKs are given by the Fourier coefficients of f. In other words, the CKs are exactly given by this formula here. This is going to be an easy homework. It's not a terribly deep result. It's really something I could have given as an easy 511 exercise. But it's probably one of the only rigorous results that basically come for free. You can actually, if you impose stricter and stricter conditions on summation, like let's say, k to some power, absolute value of ck converges, then you can say things about differentiability properties of f. I don't think I'm going to get into that really, but this kind of thing, imposing really strict conditions on ck, kind of L1 type conditions, is really, that's the only way to get really easy, quick, rigorous results. So, okay, so now in general, let's make the statement that f of x equals this Fourier series where this, we're plugging in the Fourier coefficients for ck. So by that I mean it's a statement, so there's really no reason why it should be true in general. Maybe it's true, maybe it's not. Anyway, so the first question we're going to look at, when does this converge pointwise? When does it converge uniformly? And actually, I should say maybe not. Maybe I'll look at imposing stricter conditions on ck when that kind of defines differentiability properties of f. Maybe I'll make that as a homework. But let's see. Anyway, right. When does this Fourier series converge pointwise? When does it converge uniformly? If it does converge at all. If it doesn't converge, can we still approximate f by the linear combination of these complex exponentials, or equivalently by sines and cosines, in the way that we originally wrote Fourier series? Okay. When does the Fourier coefficients uniquely define f? Okay. All right. So before I go to any other questions, particularly question 1 was looked at carefully in the mid 1800s, mid to late 1800s, and yeah, it was looked at by people like Jordan, same Jordan as Jordan Holder in group theory, Riemann, Dirichlet, it's the famous Dirichlet from number theory. And I should mention, it's quite historically interesting that Riemann, in coming up with Riemann integration, wasn't interested in calculus 1 pedagogy. He was interested in coming up with a rigorous integration process to rigorously study Fourier series. A little interesting bit of history there. Okay, so getting more into the 20th century, and absolutely Fourier series spurred the development of LP theory. So let's say f is an LP of 0 to 1, and let's say we periodically extend f almost everywhere to the whole real line. What do I mean by that? Well, we take f, define it almost everywhere on 0 to 1, and then we just say, well, on 1 to 2, modulo set of measures 0, f looks exactly the same as it does on 0 to 1. On -1 to 1, modulo set of measures 0, f looks exactly the same on -1 to 1 as it does on 0 to 1, and this is pointwise. And we just do that for the whole real line. We don't care about sets of measures 0, so on each interval, 1 to 2, 2 to 3, -2 to -1, et cetera, we don't care how we define it as long as it's the same as f on 0 to 1, modulo set of measure 0. And the norm for this LP space is just the normal, usual LP norm on 0 to 1. All right, so if f is an LP, we probably should abandon any, there's no hope of pointwise convergence. It just doesn't make sense. But we maybe have convergence in LP. Okay? And issues like this are quite useful in modern theory of PDE, particularly similar questions for the Fourier transform, which I'll mention in a second. Anyway. And it turns out that you do have convergence in LP if P is bigger than 1. And if P equals 1, you just have convergence in measure. Okay? You don't quite get L1 convergence. And it was kind of interesting that this was answered in the early 1900s by F. Ries, R-I-E-S-Z. Can't really pronounce his first name too well. It's a Hungarian name. But using complex analysis, and that is not very good because I have nothing against complex analysis, but the challenge and the reason why it's not satisfactory is because basic complex analysis techniques do not easily extend to higher dimensions. The theory of complex analysis in higher dimensions is very challenging. On the other hand, you still want techniques to study Fourier series in higher dimensions. So in the 1950s, people came up with a lot of techniques to study Fourier series via techniques that are much more akin to the things we looked at in real analysis, AMAT 510A, which extend very easily to higher dimensions, which is not hard to imagine because Lebesgue integral in higher dimensions is basically the same as the Lebesgue integral in the real line. We just do everything in the real line because it's just a little bit easier, but it's basically the same. Okay. And that's the approach we're going to take. We're going to try and look at this question 3 for a good chunk of the semester using techniques that don't involve complex analysis. All right. Okay, so a much harder question, which is very natural, but we're not going to go anywhere near because it's just very challenging, is for what P do we have pointwise convergence almost everywhere of Fourier series? The answer is P is bigger than 1. When P equals 1, you can actually have a L1 function whose Fourier series diverges at each point. That was actually proved surprisingly early by Kolmogorov, the famous Kolmogorov from probability theory. We might get to that. I don't remember how easy that example is, but we might. I think we'll get to that. I think it uses some functional analysis, actually. You just prove the existence of that function. But anyway, yeah. So this question here was answered in the affirmative when P equals 2 only, actually. By Lennart Carlesson, C-A-R-L-E-S-O-N, if you're, you want to look him up. And this was done in the 1970s, believe it or not. And even then, it took mathematicians 10 or 20 years to really grasp the techniques that this guy initiated. I mean, the famous Charles Pfefferman, a Fields Medal winner, 10 years after Carlesson came up with his proof, Pfefferman came up with an Annals of Mathematics paper that just essentially clarified Carlesson's proof in the 1980s. So, yes, and the techniques are called time frequency analysis here. I don't want to go anywhere near that, but anyway. Okay, so last but not least, a much easier question is if f is not one periodic, can we still define Fourier series somehow? Assuming other things on f, other conditions on f. So if f is not one periodic, obviously each term in the right-hand side is one periodic. So if this converges, this pointwise, or this is going to be one periodic. So if f is not one periodic, it doesn't make sense, the Fourier series, to even ask this question. You know, does it converge in any way, really? And the answer is yes. What you do is you abandon Fourier series for the Fourier transform. And what is quite interesting is that you can actually derive the Fourier inversion formula from Fourier series, from the Fourier series formula. So you can actually take this here, assume this is true, kind of do some very clever manipulations to this to get what you would expect for the Fourier inversion formula, which that is really quite interesting. And that is actually from the book Tolstov Fourier series, that little cheap Dover book that I'm going to do that. I'm going to take that from that argument going from Fourier series to the Fourier transform. Okay, so we're going to start on the path to answering question 1. So first of all, let's say I have an L1 function on 0 to 1, and we periodically extend that to all the real line almost everywhere in the sense that I described earlier. Then I claim that the integral from 0 to 1 of f of x dx is the integral from, well, really the integral over any interval of length 1. I quantify that by saying it's the integral from a minus 1 to a for any real number a. And this is actually very easy to prove if you assume the change of variable formula for Calc 1 holds for the Lebesgue integral, which it does. And actually, if f was Riemann integrable, you could actually give this as a Calc 1, like a honors Calc 1 assignment. Really, all you do is a change of variables and use the one periodicity property of our function. Otherwise, it's really nothing to it. Okay. And by the one periodicity, I mean, f of x plus k equals f of x for almost all x, which is perfectly fine for integration purposes. Okay, so assuming this is true, the approach we're going to take to answering question 1 is we're going to associate to f the partial Fourier series, k equals minus n to n for a positive integer n, and study the partial Fourier series through a very natural integral operator. And you can often do this in analysis. This is just an approach that often works, so it's a very fruitful way of thinking. Right, this way of thinking is the reason why Professor Bachanu in his topics course studied a lot of the same tools that we're going to study. Okay. I should maybe mention, we're going to study similar things to what Professor Bachanu studied in his course, some similar things. But I'm going to go way more into detail because what's more important, I think, for you guys is to really get your hands dirty and really, get used to the tools that are used to study Fourier series and the Fourier transform, because it gives you kind of a different way of thinking and looking at various problems and analysis. And that's really the heart of this course. It's just teaching you a way of thinking about problems and analysis that might be different than what you've done before. This way of thinking doesn't always work, but sometimes it works. Anyway, so how do we do this? That's very easy. We know what f hat of k is. We have a formula for it. And I should also mention that because f is an L1 of 0 to 1, this definition for f hat is perfectly fine. There's no issue. This is a perfectly fine measurable L1 function for each k. Because this is how, obviously, as modulus 1, the exponential, the complex exponential. So I integrate. I bring the complex exponential inside. So this partial Fourier series is defined for all x on the real line. There's no issue. It's a finite sum. This is a perfectly nice complex number. And this here is defined for all x. So there's no ambiguity at all. So perfectly fine. This is a constant with respect to integration. Combine the complex exponential and interchange sums and integrals. The finite sum, no issue there. Let's call this dn of x minus t. Big D is for Dirichlet. It's called the Dirichlet kernel. And anytime we have generally speaking, like a concrete function of two variables times what is more or less an arbitrary function of one variable, and you integrate that, that concrete function of two variables is called a kernel. It's a kernel for the integral operator that you're working with. All right. So we want to do a little bit of manipulations to this. So let's say u is x minus t. Do a u substitution. All right. So, right, we go from, instead of 0 to 1, it's x minus 1 to x. Right. Right. So, right. So we have dn of x minus t is dn of u. And we have, well, t is going to be x minus u. So dn of x minus t, sorry, f of t is f of x minus u. And this whole thing here, for each fixed x, well, first of all, f of x minus u for fixed x, that's measurable, perfectly fine for almost every u for each fixed x. So integration, this is fine. This is a perfectly fine L1 function here. This obviously is bounded in modulus by 2n, actually 2n plus 1. But dn of u, replace x minus t with u, that's obviously one periodic. And for each fixed x, this is certainly one periodic. Again, for almost every u. Right. So this is a perfectly fine L1 function. That's one periodic. So as we mentioned, the integral over any interval of length 1 is the integral over 0 to 1. Okay. And let's just go back to u. Go back to t. We started with t, so why not? Okay, so let's now look at some properties of this Dirichlet kernel. I claim that the integral is just 1, and that we can get a nice closed form formula for dn of t. I mean, in some sense, it's not so nice. It's a, this function, if you graph it for large n, wildly oscillates from positive to negative. And it just gets more and more and more oscillatory as n gets larger and larger and larger. And it does have a removable singularity at t equals 0. Just use L'Hopital's rule to get that. It would just be just 2n plus 1, or rather, sorry, it's going to be, yeah, it should be 2n plus 1 as t goes, or sorry, 2n plus 1 times pi as t goes to 0. But anyway, so the proof of 1 is very easy. You just integrate, well, use the definition of dn of t. K equals minus n to n. This is going to be, well, sorry. You just use the, had a brain fart there. So you just use the definition of dn of t, interchange sums and integrals. It's a finite sum, so there's no issue there. So integrate 0 to 1, e to the pi I k t dt. That's going to be 0 if k is not equal to 0. We did basically that calculation already. And it's 1 if k equals 0. So the whole sum collapses into 0 to 1 integral dt, which is 1. Okay, so this is a little more involved, property 2, but it's very elementary. It's a really beautiful little argument here. So write down the definition and factor out an e to the minus 2 pi I n t. And you can check trivially that has the effect of not changing what I'm summing, but it changes what I sum over. Instead of minus n to n, it's going to be from 0 to 2n. Okay, and notice that I can write e to the pi I kt as e to the pi I t raised to the k. And I want to do all this so that I can use the finite geometric series formula. Sorry about that. It's a little better. Okay, so let's say this is r here. So I have k equals 0 to 2n, r to the k. We could just use the finite geometric series formula here. It's 1 minus r to the 2n plus 1. R to the 2n plus 1 is obviously e to 2 pi I 2n plus 1p. So hopefully you're convinced of the utility of using complex exponentials over sines and cosines, and why even applied mathematicians often and engineers want to use complex exponentials. And then at the end of the day, go back to everything being real. But anyway, right. So, right, and it's also in the denominator 1 minus r for the finite geometric series formula. So it's just not much to say there. This is r 1 minus r. All right, so I want to do one last thing so I can get this in terms of signs. So I multiply and divide by e to the minus pi I t, and then I'm going to distribute the numerator, and I'm going to distribute the denominator. Right? And when I do that, when I distribute the numerator and I distribute the denominator, I'm going to get the following, which you can either plug into the formula for sine, or just after multiplying and dividing by -1, multiplying the top and bottom by -1, rather. Or you can just write the complex exponentials out in terms of sines and cosines. You'll see the cosines cancel, the i's cancel in top and bottom. However you do it, you get sine 2n plus 1 pi t over sine pi t. Okay, so what's the utility here? Well, I can write f of x as 1 times f of x, not very deep. This is for, we're going to soon assume f is defined for all x. So let's assume x is defined, sorry, f is defined for all x. Or if you really want, just this is for almost every x, if f is an L1 of 0 to 1 and it's 1 periodic, whatever. Okay, so 1 is this integral here for each n. Again, we're saying for almost, this is for almost every x, so f of x is well defined. If f is an L1, then f of x is finite almost everywhere. We learned that in AMAT 510A, so I can bring f of x inside the integral. It's a constant for the purposes of this integral. All right. And what's really nice is that this actually is not too far off. It's quite amazing, actually. And this is typical of other similar arguments. That this here, f of x, is not that far off from Sn of f of x, the partial Fourier sum. And actually, it's basically the same, except instead of f of x, we have f of x minus t. So what this means is that we've got absolute values here. So the absolute value of f of x minus Sn of f of x, which we hope goes to 0 as n goes to infinity in some way, pointwise, uniform, something, in some way, that is going to be given by, it's equal to this, sorry, I'll get rid of that here. It's going to be given by this integral right here, just adding these two integrals up. Okay. All right, and that's what we're going to look at this next time. We're going to particularly look at this interesting function, and we'll see the main properties of this, what makes it special, and why it's reasonable to think that as n goes to infinity, this should converge to 0. So we would expect Fourier series to exist, but it might not be clear from this here why we should expect this to be 0. But all right, this is a good place to end. So long, take care, and I will hopefully see a lot of you on campus, or if not, during office hours and Zoom. All right, stay safe, bye-bye. Expect a new video to come pretty soon.